Have you ever wondered why some of the newest AI data centers are being built with water pipes running directly to the server racks? For decades, data centers were cooled with air. Cold air went into the front of the server rack. Hot air came out the back. The cooling system removed that heat and the cycle repeated. And for many years, that worked just fine. But then AI arrived. Today's artificial intelligence servers consume dramatically more power than traditional servers, and wherever there's power, there's heat. A lot of heat. The cooling methods that worked for conventional data centers are now reaching their practical limits. In this video, we're going to explain why AI is changing data center cooling forever, how liquid cooling works, the different types of liquid cooling systems being deployed today, and why many experts believe air cooling alone may soon become a thing of the past for high-density computing. Let's get started. Why AI creates a cooling problem? To understand liquid cooling, we first need to understand what changed. Traditional enterprise servers might consume a few hundred watts of power. A rack filled with those servers could consume anywhere from 5 to 15 kilowatts. Modern AI servers are completely different. Many contain multiple GPUs working together to process enormous amounts of data. These GPUs consume tremendous amounts of power. A single AI server can easily consume 10, 20, or even more than 100 kilowatts depending on its configuration. Now imagine multiple AI servers installed within a single rack. Rack densities that once averaged 10 kilowatts are now reaching 50, 80, and even well over 100 kilowatts per rack. Some of the newest AI deployments are approaching 200 kilowatts and beyond. The challenge isn't supplying the power. The challenge is removing the heat. Because every watt of power consumed by a server eventually becomes heat that must be removed from the building. And that's where traditional air cooling begins to struggle. Air is actually a poor heat transfer medium. It can carry heat away, but it requires very large volumes of airflow. As server densities increase, cooling systems must move more and more air through the rack. Fans become larger. Fan speeds increase. Power consumption rises. Noise levels increase. Eventually, there simply isn't enough airflow available to remove the heat efficiently. Think about trying to cool a red-hot piece of metal. You could blow air across it, or you could place it in water. The water removes heat dramatically faster. The same principle applies inside an AI server. Water can absorb significantly more heat than air. This allows cooling systems to remove large amounts of heat using much smaller volumes of fluid. That's why the industry is increasingly turning to liquid cooling. Liquid cooling simply means using a liquid to remove heat from electronic equipment. Instead of relying entirely on air to transport heat away from processors, liquid is brought much closer to the source of the heat. The liquid absorbs the heat and carries it away where it can be rejected through the facility cooling system. The goal is simple: remove heat as close to the source as possible. The closer you get to the processor, the more effective the cooling becomes. Today, there are two primary approaches being used in AI data centers: direct-to-chip cooling and immersion cooling. Let's look at each one. Direct-to-chip cooling is currently the most common liquid cooling technology being deployed in AI facilities. In this approach, a cooling device called a cold plate is mounted directly onto high heat-producing components such as CPUs and GPUs. The cold plate contains small internal channels. Cool liquid flows through these channels. As the processor generates heat, that heat transfers into the cold plate and then into the circulating liquid. The liquid carries the heat away from the server. The warmed liquid leaves the rack and returns to a cooling distribution system where the heat is removed before being sent back again. It's very similar to the cooling system inside an automobile engine. Heat is collected from the engine and carried away by a circulating fluid. The major advantage is efficiency. Instead of cooling the entire room, you're cooling the exact components generating the most heat. This allows much higher rack densities while reducing the amount of airflow required. However, most direct-to-chip systems still require some air cooling. Components that aren't connected to cold plates still need airflow for cooling. As a result, many AI data centers use a hybrid approach combining liquid cooling and air cooling. How the liquid reaches the rack. One question many people ask is, how does the water actually get to the server rack? Most modern liquid-cooled data centers include a cooling distribution unit, often called a CDU. Think of the CDU as the interface between the building cooling system and the IT equipment. The CDU circulates coolant through the racks while maintaining proper temperature, pressure, and flow rates. The building may use chilled water or another cooling loop. The CDU transfers heat from the server coolant into the facility cooling system. This separation helps protect sensitive IT equipment while allowing the data center infrastructure to operate safely and efficiently. Piping networks distribute coolant throughout the white space, much like chilled water systems distribute cooling throughout commercial buildings. In our example here, we have a chiller, serving both a chilled water crawl unit and the cooling distribution unit. The heat is then rejected by the chiller through a condenser water loop served by a roof-mounted cooling tower. Immersion cooling. Now let's talk about the most extreme form of liquid cooling, immersion cooling. Instead of bringing liquid to the server, immersion cooling places the server directly into the liquid. The servers are submerged inside tanks filled with specially engineered dielectric fluids. These fluids do not conduct electricity. That means electronic components can operate safely while completely immersed. As the servers generate heat, the surrounding fluid absorbs it directly. The warmed fluid then transfers heat to a cooling system. There are two primary immersion cooling methods: single-phase immersion cooling and two-phase immersion cooling. In a single-phase system, the fluid remains liquid throughout the process. Heat is absorbed and carried away through circulation. In a two-phase system, the fluid actually boils when it contacts hot components. The vapor rises, condenses on a cooling surface, and returns as liquid. The process repeats continuously. Immersion cooling can support extremely high power densities while reducing the need for server fans and traditional airflow management. However, it introduces new challenges related to maintenance, equipment compatibility, operational procedures, and facility design. Because of these factors, immersion cooling remains less common than direct-to-chip cooling, although interest continues to grow. Removing heat from the server is only half the battle. The heat still has to leave the building. Once heat is transferred into the liquid cooling system, it ultimately moves into the facility's mechanical infrastructure. That may include chilled water systems, cooling towers, dry coolers, fluid coolers, or other heat rejection equipment. The exact configuration varies from one facility to another, but the principle remains the same. Heat travels from the processor to the liquid, from the liquid to the cooling system, and eventually to the outdoors. No matter how advanced the technology becomes, the laws of thermodynamics still apply. Every watt entering the data center must ultimately leave as heat. AI isn't slowing down. Training larger models requires more processors. More processors require more power. More power creates more heat. Many experts believe future AI facilities will routinely operate at rack densities that are simply impractical for traditional air cooling alone. Liquid cooling allows data centers to support these higher densities while improving cooling efficiency. It also helps reduce fan energy, lower airflow requirements, and make better use of available floor space. That's why nearly every major AI infrastructure provider is investing heavily in liquid cooling technologies. The question is no longer whether liquid cooling will be used. The question is how much of the data center will eventually be liquid cooled. For decades, air cooling was the backbone of the data center industry. But artificial intelligence is changing the rules. As rack power densities continue to rise, liquid cooling is becoming one of the most important technologies enabling the next generation of AI computing. Whether it's direct-to-chip cooling using cold plates or full immersion cooling using dielectric fluids, the goal remains the same. Remove heat more efficiently so processors can operate at higher performance levels. And as AI continues to expand, liquid cooling will likely become one of the defining technologies shaping the future of data centers. If you found this video helpful, be sure to check out our HVAC and plumbing estimating spreadsheets to streamline your construction bidding process. Check out our HVAC, electrical, and plumbing construction forms to help you run your business, and explore our online courses for in-depth training.